Okay, happy Tuesday, PreCalc kids. So we are on section 4.4, part 2. So when you're looking at Hernie's website, there's some stuff that's from 10.3, and that's in your Demana book. But we start with the stuff on limits out of our packet. So the packet that you guys have that we scanned to you, and you're looking at section 4.4. So we kind of did all of those big theorems about how limits and calculus in general are beautiful. And now we're just practicing a bunch of stuff. Some of it will be a little bit of review that we already did on Monday, and then some of it will be new. So a theorem that we did not go over that I think is important to go over, and we're doing an example right with this theorem, is theorem 6. So remember that in the packet they number them. It's what they do in calculus 2. It's not like we're ever going to say what's theorem 6. You just need to know how to use it. So theorem 6 says, for all c values, as long as c is greater than 0, the limit as x approaches c of the square root of x equals the square root of c. So basically, they're saying that you have to have positive value here, because if you had a negative value and you tried to substitute it in, right, you would get i's. And really, this is what this is saying. It's kind of like that one that is the limit as x approaches c of x. And we can just go, oh, then we just put the x in place of the c, and we just substitute it in. And that's where we get to drop the limit notation. It's really saying the same thing, that you can do that on a square root. Okay? So with that knowledge, let's look at this example. So the limit as x approaches 9, and I know might be a little hard to read, we're running low on our markers, of the whole entire expression 4 minus the square root of x over 25 plus x squared. So remember that there was a long way to do this, and just because it's Tuesday and we're really excited and we love those theorems, we're going to do this problem first the long way, and then we'll have appreciated it for today, and then truly after we do this last one the long way, every other time we'll do it the shortcut way. Okay, but I just want to make sure you understand it comes from somewhere, so you get the big idea, which is the most important thing in calculus. So remember that if I look at this big picture, I see a quotient, right? I see something divided by something, big picture-wise, a big numerator divided by a big denominator. And the limit of a quotient is the quotient of the individual limits. So I'm going to break this apart and say, well, let's write it as the limit as x approaches 9 of just the numerator, 4 minus the square root of x, and do a great big fraction bar, divided by the limit as x approaches 9 of just the denominator, which is 25 plus x squared. Calculus is beautiful, and we can use one of those theorems that way. Well, now we have a difference on top, and we're doing a limit of a difference, so that's the difference of the individual limits, and a sum on bottom, and if we're doing the limit of a sum, it's the sum of the individual limits. So I'm going to work across, so I'm going to do a little arrow to show, this step simplifies to my next step. So I'm going to break it apart as the limit as x approaches 9 of just 4 minus the limit as x approaches 9 of just the square root of x. So if we're breaking it apart and saying the limit of a difference is the difference of the individual limits, then each individual limit has to have the limit notation there. Remember, this is how the long way goes. All over, something similar in the denominator, the limit as x approaches 9 of just the constant 25 plus, if this is a sum, I'm going to break it up as the sum of the individual limits, the limit as x approaches 9, and we did this on the last video, but do you guys remember that x squared, something to a power is just that something times itself? So I'm going to kind of do two steps at once and break this sum apart, but also say this is the limit as x approaches 9 of just x by itself times the limit as x approaches 9 of just another x by itself to represent x squared, and then extend that fraction bar. And the reason that I wanted to do that all in that one step is now I actually have all those small, simple pieces that I should have memorized by definition by theorem 3 that tell me what all these limits evaluate to. And when I'm evaluating them, the word limit goes away. So the limit as x approaches 9 of a constant 4. This is really just the graph y equals 4. It doesn't matter what x I go to, but I'm approaching 9 from both sides, from the left and from the right. As I approach 9, I'd be approaching the number 4. So the limit of a constant 4 is the constant 4. Minus the limit as x approaches 9 of the square root of x. Oh, that's a theorem we have still right here, right on the board, right above here. Oh, you can just substitute this in. So what did this turn into? The square root of 9. Plugging in that c value in place of that x. The limit as x approaches 9 of another constant, the constant's 25, we'll go to the constant 25, plus the limit as x approaches 9 of x, oh, the limit as x approaches c of x, oh, don't you just put your c in place of that x? So both of these are going to go to 9. So trying to make you appreciate those theorems one last time before we just go straight to the shortcut. So if we've evaluated each one of these limits where I've changed like the blue and drew a black arrow through it, then now all we have left is 4 minus the square root of 9 over 25 plus 9 times 9. Well, the square root of 9 is a perfect square, right? So that simplifies and goes to 3. So we have 4 minus 3 over 25 plus 81. Multiplication happens before addition, so 9 times 9 is 81, which would leave us with 1 up top in the numerator. And then we would add that sum down in the denominator and get 106. So this limit answer is 1 over 106, which we kind of briefly talked about this, you guys, in the last video. Like, thank goodness we can do limits algebraically. How would we know graphically that the closer and closer and closer we get to 9 of this rule, the closer and closer we're getting to the y value of 1 over 106? You would never know that. You have to be able to do it the algebra way. So that's the long way. And let's go straight to the shortcut way. And then, like I say, I won't ever make you do the long way again. But I wanted you to appreciate it one more time and really see it one more time and understand that's why it works. So rewriting the original problem, the limit as x approaches 9 of the rule 4 minus square root of x over 25 plus x squared. All right, so if we appreciate all of this stuff and we're like graduating into just going the shortcut way, then we're thinking, oh, the first thing that we try with limits as x approaches a c, this is something you'll keep hearing us say over and over again, is direct substitution. So let's see what happens if we directly substitute. Well, if we're directly substituting, we're evaluating the limit. The limit notation goes away because we're taking the limit. We're evaluating the limit. So the 4 would still be there, minus, we're replacing every x we see with the 9. So in this case, the square root is the house over top of that replacement. So the square root of 9 over 25 plus, I'm replacing this x in the denominator also with 9, and it's still squared. Well, remember we talked about just working vertically down and simplifying it as you go. You don't need to rewrite it with limit notation at the end. That will screw you up. So this would be 4 minus 3, because I still have that perfect square, over 25 plus 81. And don't I get the exact same answer I had before, which is 1 over 106. But in a much shorter way when you don't have to break it up the long way. So of course we don't want you to have to do this. That was like for a couple of problems that hopefully you did on last night's homework. And this is just like one extra chance to see it. But from here on out, practice test, when you do your real test, the first thing that you're going to try with limits as x approaches a c is direct substitution. And if you get a number value, you're good. It could be a number value, it could be 0, it could be something kind of crazy like this, it could have a pi in it or a radical in it. As long as you don't have division by 0, you should be fine. It could be negative, all those things. And sometimes you get an expression in terms of numbers and letters like A's or H's or whatever, depending on how the original problem starts. Okay? So it's kind of like a review, and now we're getting into the new stuff. So with the new stuff, let's talk about what happens if we don't just get a number, if we do get division by 0, and what we're going to have to try in the algebra world to be able to evaluate limits that just don't work with direct substitution. I mean, it can't just be that easy. Even if you had a long way and a short way, now you guys know the short way, it just can't be that easy all the time, right? There's got to be more to it than that. So when we're doing a limit as x approaches c, and I'm even going to draw the arrow that we kind of read that way, and c is a constant, let's kind of talk about what your like steps should be, what your menu should be that you follow. So the first thing that you should try is you should try direct substitution. That's what we just did on that last example. And if direct substitution works and you get a number value out, you're done. I mean, you're hoping that this is what happens every single time. It's not going to, but that's what you're hoping happens, okay? So if you try direct substitution and you get a number value, then you get to drop the word limit, you evaluate it, boom, you move on. Now you can always do it the shortcut way. So if you need me to even say, now it's okay that you always go straight to that shortcut way, that's fine. Second thing that we're going to try. If you try direct substitution, but it doesn't give you a number value because you end up getting 0 divided by 0, which a lot of times this you're kind of doing mentally. You're kind of mental mathing that and going, oh, this would give me 0 up top and this would give me 0 in the denominator. You're not really necessarily writing it, but you can tell that it's not going to give you a numeric value. You're going to get division by 0, which you guys know is a big no-no in math. Then we have to do something different. we have to do some sort of algebraic manipulation.
Finagle,
as Hernie likes to say. Right? And that could be a plethora of things, and that's really what this second part of section 4.4 is all about. Getting used to doing some sort of finagling first. So in purple, right? All right, so some finagling ideas. Definitely factoring is probably going to be at this level, at the pre-calc level, the main thing that you're going to do. That could be all sorts of factoring, you guys. Pulling out a GCF, looking for a difference of perfect squares, doing creative factoring that we're going to talk about in a minute, looking for sum or difference of cubes, which means you still need to know those formulas. Factoring even possibly something to a higher degree using synthetic division. Like it could be any level of factoring and multiple layers of it. Okay? Sometimes you do something with a conjugate where you multiply by the exact same two terms with the opposite sign, and that could be the conjugate of the numerator or the conjugate of the denominator. So kind of know like that will have its own little place and its own little thing that we talk about. It's somewhat similar to rationalizing a denominator. That could even be an option to try and get rid of a bad factor and get rid of the division by 0. Okay, and then I already kind of mentioned even possibly synthetic division. That really is going to help you factor. It could be something with fractions in an LCD, so then maybe you can copy dot flip and get a bad factor to go away. But the idea of any of those finagling things is you're trying to get rid of the division by 0, trying to get the bad factor to go away. If you can finagle it, and you have to keep the limit notation while you're finagling and get rid of that bad factor, then you can go back to this. Then you can go back to direct substitution, you get a number value, and you're done. Okay? And then kind of the third option, and everybody forgets about this one, huh, Mr. Herning? Is if you try direct substitution and you end up getting a number divided by 0. That's different than 0 divided by 0. That means graphically that you have a vertical asymptote going on. Because if you got 0 over 0, do you guys remember like graphically that you have a point discontinuity, you have a point disco, and that's why we were saying to do some sort of finagling, because sometimes that goes away and then you still are approaching a target for your limit, even if your function's not defined because you have an open dot. But if you get a number divided by 0, graphically you have a vertical asymptote there. And if you have a vertical asymptote going on right there, then the way that you're going to have to evaluate limits if you have a number divided by 0 is what we call sign analysis. Oof, I can't spell analysis if I try and like write it. Capital letters. Analysis. Here's the Y. There we go. And for whatever reason, like I say, this is the one that a lot of people tend to screw up on. They just completely forget, and then they say the answer's 0. No, you can't divide by 0. Or they say the answer's undefined, and no, that doesn't cut it as an answer, and I don't know like what happens. But I would watch out for that one. That is the one that we tend to like do a lot wrong. So we'll talk about that when we get there. But before we even get to examples, I need to show you guys a trick with factoring. I always call this creative factoring. And then if we were really in school doing this, like in the classroom, we would talk about it and you would say, Ms. Ryan, why didn't you teach us this like way back when we learned how to factor? And I would say, because you weren't mature enough to handle it way back when. But now you're finally mature enough. Like you're in pre-calc at scored 4, now you can handle it. So if I tell you to factor x squared minus 5. And I say, okay, here's an expression, we're going to factor this. Or if Hernie and I gave this to you on like a review assignment and you had a big group of factoring problems, a lot of you would say, no, not factorable. There's nothing to do. There's not a greatest common factor between these two terms. This one has a variable, this one doesn't. I have a difference, but 5's not a perfect square, even though x squared is. It doesn't have cubes going on to be a sum or difference of cubes, so you'd be like, yep, not factorable, move on. Remember, you even have factoring by grouping as an option if you have 4 terms sometimes. Because really, this can factor. I mean, if I go, it's a difference, and x is a perfect, or x squared is a perfect square of x and x, and some of you go, but 5's not a perfect square. Well, what times itself gives you 5? Oh, I don't know, square root of 5 and square root of 5? Like, couldn't that work? And then still opposite signs? We can check factoring by refoiling or big distributive property, x times x is x squared. The outside and inside would cancel because that's the idea of the conjugate thing right there. And then positive root 5 times negative root 5, wouldn't that give us negative square root of 25? But that's really just 5. So it actually does factor. But way back when you learned difference of squares, like you weren't mature enough to realize that and understand that and feel comfortable with that so much. And you didn't need to until now. So even if I extended this problem and said, okay, let's factor something that looks linear, where typically if we get down to something that's linear, we're like, yeah, we're done, no more factoring. But maybe we need to factor x minus 3. I could factor x minus 3. That two-term binomial could factor as the square root of x times the square root of x. They would multiply back to just give me x. Opposite signs, plus minus, so the outside would cancel on a binomial, right? And we're factoring it into a product of two binomials. And how about square root of 3 and square root of 3? Because that would multiply back to just give me 3. So really, we have this kind of idea of creative factoring. And we need to know that because maybe we'll have to use that in some of our finagling on different problems. So watch for that. Just throwing it out there. Okay? So we're going to do some more examples where we're going to not just be able to have direct substitution with the shortcut work and be done. Where the big idea is we're going to focus on this, if it's 0 over 0 and all of these options, or if it's a number divided by 0, then we'll try that whole sign analysis. The notation is what's really probably the most difficult of anything. So if you're struggling on the notation, please go back and rewatch the videos. Because what we're showing to you guys is good notation. And I know it's hard not being able to ask questions and, go up to the board and have us watch you and fix your notation. But we're just going to have to do what we can do right now during this time where we're doing online learning. Okay? So let's just kind of blast some out in other examples. This very first one I'm going to do with you, I'm showing you this way on purpose because I think it's on problems 13 through 16 in this format. So I think in your packet on problems 13 through 16, they give you some notation like this. F of x equals x squared minus 4 over x minus 2, and then they give you a semicolon and they say c equals 2. And in the directions, they're asking you to find the limit as x approaches c of this function. So the first thing you want to do is you just want to change it into the limit notation. So we want to do the limit as x approaches our c, here's our c, of this rule. Oh, so don't put f of x there because we want to put in our rule. Oh, of the rule x squared minus 4, the rational function over x minus 2. So what's the first thing that we try? If we have a limit as x approaches c. Mr. Herney, what's the first thing we try?
Direct sub.
Okay, so if we try to do that, immediately, and a lot of people start with the denominator, because if the denominator seems good to go, you're probably good to go. Well, if I just mental math this, wouldn't 2 minus 2 give me division by 0? So we're like, uh-oh. But I also want to analyze what's going on top so I can determine, is this an algebra finagle problem or is this a sign analysis problem? I'm kind of just mentally thinking this through. And it's pretty nice numbers to work with. Well, 2 squared would be 4 because I'd have to evaluate my exponents first, and 4 minus 4 would also give me 0. So if I have 0 over 0, direct substitution is not going to work. We can't divide by 0 in math, and if I have 0 divided by 0, we're thinking, well, let's try and do some sort of finagling. So most of you will go, oh yeah, I see this. I have a difference of squares, and if I factor this, this guy will cancel with one of these guys on top. And you can immediately see that. That's awesome. But if your notation sucks while you're getting there, then you're not getting points, people. Come on. So we're still having to carry the limit notation, because if we haven't substituted, we haven't evaluated the limit. We're finagling right now. We're changing this into a more friendly calculus form to be able to do direct substitution. So you carry the limit as x approaches 2, and we factor the top as a difference of squares, x plus 2 times x minus 2. And we still have the bottom, which is that two-termed binomial x minus 2. And lo and behold, we get this bad factor to go away. Or graphically, doesn't that mean that this is a point disco at x equals 2? Right? So now this graph is just going to behave like the graph of x plus 2. So the limit as x approaches 2 of just the linear piece x plus 2. Well, now I don't even have a denominator, so I'm not even going to have anything going on with division by 0. So I should be good to go. I should just be able to now directly substitute. Remember, calculus is beautiful. Yes, if we were doing this a long way, we would write the limit as x approaches 2 of just x plus the limit as x approaches 2 of just 2. We don't have to do that anymore. We appreciate the long way. We're just going, hey, we just get to replace this into here. That's where the word limit goes away. We are evaluating the limit, and 2 plus 2 gives us a limit answer of 4. So this is the best notation. Okay, working vertically down, showing the work. You don't have to really go back and rewrite anything. I think everybody wants to do that. If you were going to do that, you would have to go back to the original problem, the limit as x approaches 2 of all of this rational function, rewrite the whole thing, and say it equals 4. So our word of advice is just do it like this. Once you directly substitute and you replace your x's with numbers, the word limit goes away, and you take your limit.
Yeah, you don't even have to have any equal signs. You see
Right.
how there's no equal signs? The only time you need equals is now if you start going from left to right and you start, instead of going up, down. So if you strung this out all on one line, then you would need equal signs. But right here, just work your way down, don't even need them.
Best notation. Okay, so moving on. Example 2. I'm gonna change the markers, seeing if I can get a marker that seems not all readable
They all suck.
on the video. Mr. Harney's saying they all suck. Next one, the limit as x approaches 4 of 4x minus x squared all over 2 minus the square root of x. So we're going to do this problem 2 ways. I'm just trying to show you guys some things where we have one problem that works kind of 2 different ways depending on how you see it. Okay, so we're going to say method 1, we're going to say method 2. So first thing we try with a limit as x approaches c is going to be direct substitution. So again, I would think of this mentally and I would start in the denominator. And the square root of 4 is 2, which is a nice perfect square, but then the 2 minus 2 would leave me with a 0 down below. So we're like, direct sub the normal way where it just works and we're done is out. But we better analyze what's going on top. So when 4 minus 4 gives me 16, and then 4 squared is also 16, so when the numerator also equals 0. So if it's 0 over 0, we know it's some sort of algebra finagling. Most likely something to do with maybe some sort of factoring. Okay, so if I said factor, then I'm not evaluating the limit yet. So I'm stringing my limit notation. The limit as x approaches 4. And I think a lot of you will go, oh yeah, up top we can factor because we have a greatest common factor of x. This is why, you guys, we've had factoring on like every review assignment we've given you after every test over and over and over again, right? We're trying to do that so you're constantly practicing that all year. We would be left with 4 minus x over the 2 minus the square root of x. So I said we were going to do this 2 ways. So because we just were talking about that creative factoring that's still right here in blue on the right-hand side of the board, let's think about some creative factoring right here. So this linear binomial in the numerator, 4 minus x, typically we would say it's linear, it can't factor anymore. But maybe we could try to factor that. Because we know that 4 comes from 2 times itself, 2. So that would go with the first part of each set of parentheses. And as long as it's a subtraction sign, we can say, oh, opposite signs, plus, minus, so the outside and inside would cancel. And I just need x to come from something times itself to give me back to x. Oh, how about the square root of x times the square root of x? Still all over that original denominator. And the reason I did that is for right here. I just got the bad factor to go away. So when I keep saying the bad factor, it's the part that's giving you that division by 0. So if I have all factored form and it's all multiplication, can't I reduce out these common factors? I slice those 2 binomials out, whoop, and now I'm just down to the limit as x approaches 4. I don't even have a denominator anymore of just x times 2 plus the square root of x. So if I got my bad factor to go away and I don't even have a denominator anymore, direct sub should happen. So I'm going to plug in that 4. Now this is where the limit notation goes away. When I'm plugging in a number value, and it's going to be all numbers, that's where I'm evaluating the limit. Times 2 plus the square root of 4. Square root of 4 is a perfect square of 2. This would be 2 plus 2, which would give me 4. And 4 times 4 gives me a final answer of 16. Okay? So that's method 1 of that problem. So showing you method 2. So kind of erasing that creative factoring, but we just did that trick to help us evaluate that limit and help us do some algebra manipulation or some finagling. So I'm going to rewrite it from the start. The limit as x approaches 4 of 4x minus x squared over 2 minus the square root of x. And I still think at that first step, a lot of you would go ahead and factor the numerator, and you would pull out your GCF of x and be left with 4 minus x. But maybe you don't see the creative factoring, and you're like, I don't see that. It just didn't make sense to me. It's just not my like instant gut feeling. Well, remember how one of the things I said for finagling could be a conjugate? Well, if I look at my denominator, a lot of times it seems like with conjugates we do something where we have radicals going on. If I have 2 minus the square root of x, isn't its conjugate the same exact two terms, the 2 and the square root of x, with the opposite sign in the middle? So it would have to be addition if this started as subtraction. And if I'm going to multiply my denominator by the conjugate, I have to do the same thing to the numerator, still multiply him by 2 plus the square root of x, so it stays an equivalent fraction. So instead of maybe that creative factoring, I'm using a conjugate sort of manipulation. So if we're using a conjugate, we're going to multiply the conjugates together, because nice stuff is supposed to happen when we multiply the conjugates together. I'm not necessarily going to multiply the numerator. I'm just going to leave it in factored form. Remember, we're trying to get rid of a bad factor. So if we're trying to get rid of a bad factor, maybe let's leave the numerator in factored form. The x times the 4 minus the x, that whole thing in parentheses, times the 2 plus the square root of x, that whole thing in parentheses. Big long fraction bar, and let's go ahead and multiply the conjugates together. So 2 times 2 would multiply to 4. The outside and the inside are going to cancel. Don't even write them down. You know they're going to cancel. You're multiplying with conjugates. One's positive, one's negative, and their opposite's gone. A negative times a positive is a negative, and square root of x times square root of x is just x. Oh, and since we're in factored form, now can't we slice out the common factor, 4 minus x with 4 minus x? If a bad factor goes away, and now I don't even have a denominator anymore, then the limit as x approaches 4 of just x times 2 plus the square root of x should be okay to just do direct substitution, and then we can be done. So we would plug that 4 in just like we did before and get the exact same answer of 16. So there's method 2. Just to kind of give you 2 different options. Okay? So, next example. Truly that one's done. In the trash. Like, can't handle it anymore. Ugh. So when you guys are working through your homework on this second part, if direct substitution doesn't seem like it's going to work because you have division by 0, see what happens in the numerator. If it's 0 over 0, you're going to try some sort of algebra finagling. If it's a number divided by 0, you're going to try sign analysis. Okay? So now you saw a conjugate example. We've done some factoring examples. I am just reminding you about something really quick that I'm not doing an example fully of with a limit, but I'm going to remind you of something real quick before we move on to the last set of examples. So if I gave you 8x cubed, minus 125, and I told you to factor that, I'm hoping a bunch of you see that and go, oh, yep, there's no GCF because 8's an even number and 125 is not, so they're not going to be divisible by 2 or 4 or 8. And I don't have a variable in each thing to pull out a GCF, but maybe I can think about a 2-termed binomial, and when I see an x cubed, maybe I'm thinking sum or difference of cubes. So you guys, wouldn't this be a difference of perfect cubes? So if you have a difference of perfect cubes, and if you forget the formula, Google it, right? If it's a cubed minus b cubed, doesn't it factor into a minus b times a squared plus ab plus b squared? It's always plus b squared, and this part's always an irreducible quadratic. So there's no way that this part's ever going to factor anymore. You don't even need to try it. Once you've applied the formula with cubes, that's as far as factoring can take you. Okay? So I see something where I'm kind of uncubing it in my mind. Oh yeah, what thing cubed would give me 8? 2. And what variable cubed would give me x cubed? Oh, x, so a is 2x. What value cubed would give me 125? Oh yeah, that's 5. The signs are accounted for in the formula, so now that we know individually what our a and b are, wouldn't this factor into 2x minus 5? If it starts as a difference of cubes, the first quantity is a difference. Times a squared, but you have to square all of this. 2x the whole thing squared, or 2x times itself, 4x squared, plus AB, which is why we write them down so we can multiply right here and get their product. 10x in the middle, plus b squared, and 5 squared is 25. And remember, this part is called that irreducible quadratic. So I don't know necessarily that happens in your section 4.4 homework, but I know that in the Demana homework in section 10.3, there are some things where you need to factor cubes. So there's a little like reminder of cubes. If it's a sum of perfect cubes and it starts as addition here, this one starts as addition, this one's subtraction. It always is plus b squared on the end. So it's just these two that would alternate if it were a sum. Okay, so we're on the last set of examples. I'm just blowing through markers on this pre-calc video. Okay, maybe this blue one can make it through this last set. So directions say, find each limit if it exists. So you will start to see a lot of this phrasing, if it exists, on the end of the directions when you guys are doing limits. Okay, so kind of putting it all together. So letter A, the limit as x approaches 1 of x squared minus 25 over x minus 5. Okay, I'll give you a second to kind of write that down. Letter B, the limit as x approaches 5 of x squared minus 25 over x minus 5. Notice we have the same rule for both of those, but we're approaching a different c. And then letter C is the limit as x approaches 6 of that same rule, x squared minus 25 in the numerator, but it's an x minus 6 down in the denominator. So really what you should try to do is you should try and pause the video, try them on your own, then come back and unpause it and see how you did and how your notation's looking, right? Like that's more than anything like where you guys might need more help is on the notation. So you should pause it, try all three of those, and then come back. Okay, so I'm assuming you're back. So isn't the first thing that we try when a limit as x approaches c, a constant value, direct sum. So if I mental math this in my mind, ooh, 1 minus 5, that doesn't give me a 0 down below. So if I don't even have a 0 in the denominator, I don't have to worry about 0 over 0 or a number over 0. Shouldn't this just be that it works, like direct sub right from the get-go? Which means if I'm substituting in the 1 in place of the x, I'm evaluating the limit. I am taking the limit. The word limit goes away. I am doing the limit. 1 squared minus 25 over 1 minus 5. 1 squared would stay 1. 1 minus 25 would give me a negative 24. Over 1 minus 5 would give me a negative 4. A negative divided by a negative is a positive. And 24 divided by 4 is 6. Done. That fast. You will have some limits where direct substitution works just fine. On homework, on your test, like don't think that it's always going to be factoring. Yes, this factors because you have a difference of square, but you don't need to do that. It works with direct substitution. You're approaching 1. Like, come on. That's what step 1. Part B. Now when we try direct substitution, because we've changed our c value to a 5, now we have an issue, right? Instantly, I think a lot of you would see, oh yeah, 5 minus 5, that gives me division by 0. So as soon as I see division by 0, I'm in trouble. But I need to analyze, is it 0 over 0, so I think about algebra finagling, or is it a number divided by 0 where it's sign analysis? Well, this looks like if I plug in 5 on top, I would also get a 0. 5 squared is 25. 25 minus 25 would be 0. So 0 over 0 means probably some sort of finagling. So now it seems like a wise idea to factor. Well, we aren't plugging anything in yet. We're making our limit more calculus friendly and trying to get rid of the bad factors, so the limit notation has to string with us. So the limit as x approaches 5 of x plus 5 times x minus 5. Remember, on difference of squares, you could have those reversed, it doesn't matter, over the original x minus 5 in the denominator. And now we have a common factor. We are getting rid of that bad factor that was giving us that division by 0. And so now we should be able to directly substitute. And on the last couple of problems, I rewrote this before I substituted. It's okay notation if you realize, hey, my bad factor went away, I'm going to plug in right now, if you plug in. But if you're plugging the number in, the word limit goes away. You are evaluating the limit. And when at 5 plus 5, give us 10. Okay? Best notation is the notation that you're seeing on board. So if you did try those two on your own, and hopefully you got them right, but you screwed up on notation, like concentrate more on that notation, come back, rewatch the video if you need before you do your homework. And if you got stuck on C, that's okay because we haven't done a problem yet, like C. So C says the limit as x approaches 6 of x squared minus 25 over x minus 6. So if we try just to directly substitute that mentally, we would have a 6 minus 6 in the denominator, so we'd have division by 0. But up top, you guys, we wouldn't get a 0. 6 squared is 36, and 36 minus 25 leaves us with what, 9? Like, that's a number divided by 0. So this is a different strategy. You can factor all day long if you want and say, oh, well, I get x plus 5 times x minus 5. How does that help you get rid of x minus 6? It doesn't help you get rid of that factor. You could even try creative factoring, but nothing's going to cancel. So if it's a number divided by 0, graphically what's happening is you have a vertical asymptote, and vertical lines, remember, go x equals at x equals 6. And so this is that sign analysis stuff. Okay? And again, the notation is a little weird and a little like you have to get used to it, but the idea of sign analysis is, okay, we don't have to necessarily graph it if we can run the sign analysis and think it through. So we want to find the one-sided limit and do the limit as x is approaching 6 just from the left-hand side of this rule, x squared minus 25 over x minus 6. But then we're going to want to do the limit as x is approaching 6 from the right-hand side. So that little negative in the upper right-hand corner and that little positive in the upper right-hand corner are read from the left and from the right. Of our same rule, you got to take a limit of something, x squared minus 25 over x minus 6. Okay? So, when we're trying our limit from the left and from the right, you got to tell us what you're trying. You got to tell us what you're using that's really, 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 really close to 6 from the left. So if you make an L with your left hand, right? Here's my L with my left hand. If I were coming in 2, 6, if I thought about it on a number line, and I were close to 6 from the left side, wouldn't I be getting, like, here's 5, here's 6, really close this way? So wouldn't it be something like, oh, I don't know, 5.9? Like, you don't want to just try 5. That's not close enough. You want to try something close. So I'm going to use 5.9. And actually on this problem, to run the sign analysis, because it's easier to just think about the signs, not the final answer. If we wrote that numerator in factored form, it might help us do the sign analysis quicker, so we're not thinking about what 5.9 squared is. So if I write it as x plus 5 times x minus 5, because it is a difference of squares, all over x minus 6. Watch how quick this can be. So even though I'm not going to show really plugging the 5.9 in, I'm going to think about it mentally, and I'm going to drop the limit notation. So this would equal 5.9 plus 5. Wouldn't that stay a positive factor? 5.9 minus 5. Wouldn't that stay a positive factor? Over 5.9 minus 6, that would leave me with a negative final answer. Well, I have a positive times a positive, which stays positive, divided by a negative, and a positive divided by a negative is a negative final answer. Really what that means is around your vertical asymptote at x equals 6 from the left, you're shooting down towards negative infinity around that vertical asymptote, if you just focused on that part of the graph. Okay, so let's do the same thing as we're coming in from the right. If I were on the right-hand side of 6, right, here's 7, but I'd be coming in closer and closer and closer and closer and closer. Oh, I'd probably want to use something like, I don't know, 6.1. You do have to have this one-sided limit notation to get full credit, and you do have to tell us what you're plugging in. You're just worried about the signs, not the final number answer. So to run that sign analysis a little bit quicker, it's going to help if it's in factored form. So x plus 5 times x minus 5 up top in the numerator, that's the same thing as x squared minus 25 over the x minus 6 down in the denominator. So 6.1 plus 5 would leave me with a positive. So I'm dropping the limit notation because I'm evaluating the limit. If I'm getting the signs on the sign analysis, I'm plugging numbers in. I'm getting the limit. 6.1 minus 5 would still be a positive, and 6.1 minus 6 would give me a positive. So I'd have a product of a positive on top over a positive on the bottom, and a positive divided by a positive is a positive final answer. So that means the closer and closer and closer I get to my vertical asymptote at 6, I must be shooting towards positive infinity. Well, didn't we say back when we were doing limits graphically that you have to approach the same value from both sides for the limit to exist? Oh, that's why this was there. So you got to wrap it up. So ready for this? Ready for this crazy new notation? You guys are going to love this. So if we're going towards opposite infinities, Therefore, the limit as x approaches 6, the two-sided limit, you got to take the limit of something, of x squared minus 25 over x minus 6 does not exist. Oh, some of you will remember the Mean Girls quote where she's like, the limit does not exist because LHL, the left-hand limit, does not equal RHL, the right-hand limit. And all of those abbreviations are totally like acceptable on AP and acceptable in class. But that limit doesn't exist because you're going towards opposite targets on the one-sided limit. So the one-sided limits exist. The limit as x approaches 6 from the left is going towards negative infinity. The right-hand side limit exists. The limit as x approaches 6 from the right is going towards positive infinity. But since they're not the same, then the two-sided limit does not exist. Final thoughts, Mr. Herney?
Looks good.
Looks good? You guys will get better and better at the notation. Remember, we still have section 10.3 that's on limits out of our Demanda book. So you'll keep practicing the notation and seeing it. Rewatch a video if you need. And have a good day.